So, welcome to our tutorial on the national grid, and just looking simply at what the national grid is and how it works. Now, first thing to bear in mind is that all mains appliances that we use, anything from laptops to phones to TVs to microwaves, anything that's plugged in at the wall, all get their electrical supply from power stations across the country. And the power stations across the country are connected to our homes, where we consume electricity by something called the national grid. So it's important before we do anything to make sure we define the national grid as being specifically the network of cables. So it's the network of cables and transformers. We'll come to what a transformer is in a minute. Cables and transformers linking power stations to consumers. So that's what we mean overall by the national grid. Now, first thing to bear in mind when we're talking about the generation of electrical power, we know that electrical power is generated at power stations. So if in your notes you want to make a little sketch note of our stage one in the whole process, is that electrical energy is generated at power stations. Now, important when we think about the national grid, bear in mind some figures. So power stations can generate alternating potential difference of around 25,000 volts. Okay, so if we make a little note of that in our diagram. Now, obviously, once those power stations have generated that electrical power, the power then has to be supplied by the flow of current through cables. Now, thing to bear in mind is that when we've got electrical power traveling through cables, it has to travel a long way from the power station to a consumer in order for us to plug in the things that are in our houses and for us to consume that electricity. So what we have to do, in order for electrical power to be able to make that distance of travel, is we actually have to increase the voltage before it goes anywhere. So the electrical power that's going to be supplied to our homes, before it goes through these cables that obviously see as power cables, it goes through something called a step-up transformer. So before it goes anywhere long distance, it goes through what we call a step-up transformer. Now, as we've said, the job of the step-up transformer is to increase the voltage. So, in the case of our example, increases the alternating potential difference to around 40,000 volts. So before it goes through any of these cables, the voltage is increased. Now, current then flows through pylons and wires being transported around the country. But due to the heating effect experienced by electrical conductors, when the electrical current flows through them, these conductors can actually transfer some of that electricity to thermal energy that heats the air around them. Now, so what we have is we have some thermal energy surroundings. So some thermal energy is lost to the surroundings in the air. So what actually happens is the temperature of the air around these wires increases. These are what we call transmission cables. So as electrical current flows through these transmission cables, the resistance provided by these cables can actually increase. The cables heat up. Now, hence why the step-up transformers have been incredibly important. Because if you have a higher voltage, yeah, we call these pylons, by the way. Now, if you've got a higher voltage, higher potential difference, movement of electrons carrying electrical charge around this large circuit is more efficient. So, higher PD is more efficient. Now, if you've got this larger voltage that's more efficient, it means less of the electrical energy actually gets wasted as heat energy in the air. Because if you've got a higher potential difference, ultimately means that you need less current transfer, same amount of electrical power, which means that ultimately less energy is wasted by heating. Less energy is lost as heat to the air. So it goes through these pylons, through these transmission cables until it reaches home, schools, tower blocks, all sorts that require that energy. But obviously, it's too dangerous. The energy is too dangerous at 40,000 volts to be transmitted straight into our homes. So, before it actually can be used, it has to go through a step-down transformer. Now, doing the opposite job of the step-up transformer, what this does is it decreases the voltage. It decreases the voltage of the electricity before it's used by consumers to make it safe. So you don't plug your phone in and electrocute yourself to death. So that's actually quite important. So it decreases the size of that voltage, and it can decrease it to what we might describe things like homes, schools, and businesses. Standard UK mains voltage of 230 volts. So that's actually quite an important one because you often can be asked about that in exams. Now, so that's what the national grid does. That's what the national grid does. And it's also quite important to be analysed so that actually people who run the national grid can make predictions about the demand for energy and the demand for electrical power that is going to be needed nationally based on people's different behaviour. So I've got a little crude graph of electrical power versus time in the day. And as you'll see, there are peaks and troughs, and these are all dependent on time of the day and what people are doing. So, if you think about time of the day where we might need a lot of electrical power supplied to our homes at most, sort of 4 through 8 o'clock, as it were, when people are returning home from school or work, so returning home, school or work, sitting down, turning on the TV, switching the lights on, cooking their dinners in the ovens and in the microwaves. So it requires a lot more electrical energy. Now, why would there be a trough in terms of demand for electrical power between sort of, I don't know, 10 and 4 in the morning? It's because the vast majority of the population be asleep. So there's less demand. And then if you think about it again, same idea, there's going to be a peak the other side of the morning, where actually the vast majority of the population is waking up, getting ready for the day, boiling the kettle. You'll tell it's an amazing cup of tea, turning the toaster on, all that sort of thing, and using appliances more than they would during the rest of the day. So the important thing to bear in mind is that actually power stations have to use this data to predict when they need to meet demands of people based on their behaviour. So power stations predict need for demand based on behaviour. Important idea to bear in mind as well. So we've got an overview of the national grid. And it's the cables and transformers needed to move electricity from power stations to consumers. You have to have step up and step down transformers to ensure that that electrical power can travel long distances and it isn't lost to the environment and surroundings as wasted heat energy. And also the step down transformers to ensure that actually the electricity that enters our homes, our schools, our businesses is at a safe, usable voltage, and that voltage we put through with 230 volts on as well. And the reason why electricity can be lost through cables and pylons as it travels long distances, the electrons are moving through the cables, they're vibrating and causing the atoms and the wires around them to vibrate and heat up. The more vibrations, the more heat that is released, and therefore that comes from the movement of the electrons, and that causes the temperature of the air around these cables to increase. But if you increase the voltage, it means basically you need less current to transfer the same amount of power, and so basically it becomes more efficient. Less of that energy becomes wasted in the environment and lost as heat. So, brief overview of the national grids. Thank you for watching a little tutorial.